Let's talk about global mild solutions to the Landau equation, the non-cutoff Boltzmann equation from kinetic theory. And by mild solutions, I mean these are low regularity solutions that are global in time, close to equilibrium. And so this work is joint with my collaborators Renjun Duan, Shengyuan Liu, and Shota Sakamoto. Okay, so yeah, so this paper is on arXiv, and it was recently published online, so you can find it both of those links. Let me yeah, okay, I think that's good. So the Boltzmann equation was derived in around 1872 by Ludwig Boltzmann and also by James Clerk Maxwell. Maxwell actually wrote down the equation first, but Boltzmann derived the H theorem, and for that reason, the H theorem is predicts the convergence to equilibrium, and for that reason, the equation was really named after Boltzmann. And it takes this form, so you have TTF plus V dot grad XF is equal to QFF, where X is in a domain omega, V is the X are the spatial coordinates, V is in the whole space R3, and these are the velocities, and time is going forward. And the unknown F is a probability density in position and velocity, V dot grad XF is thought of as a free transport term, and QFF is a complicated quantity. It's called the collision operator. It's a local in T and X, and it's a quadratic non-local integral operator. So this is the equation that we'll study. And so I'll tell you a little bit about it first. So this equation models particle dynamics. It's kind of a intermediate model between a many particle system and an equation like the Navier-Stokes equations from fluid dynamics. It's typically called a mesoscopic model, and it was one of the famous Hilbert problems to derive the connection between many particle systems and fluid dynamics, and the Boltzmann equation sits in between that, and there have been a lot of very interesting and important results establishing the limit connection between the Boltzmann equation and the Navier-Stokes equations. And so we're talking about particles, and so we have particles have conservation laws in this model. So given two particles moving around with velocities v and v star, after a binary collision, these particles have outgoing velocity v prime and v prime star, and these collisions are assumed in this model to obey the conservation of momentum and energy, and that takes the form of these four equations right here. So the first equation, v plus v star equals v prime plus v prime star, is actually three equations because these quantities are in R3, and the second equation is one equation, it's conservation of energy. So since there are six unknowns, v prime and v prime star, and four equations, the set of solutions can be parameterized on the sphere sigma in S2. And there are several different formulas that you can write. One of them is written here. It's v prime is v plus v star over 2 plus norm of v minus v star over 2 times sigma. And v prime star is the same thing with the minus sign instead of a plus sign. And then, so there's a little bit of geometry that you can do, and these velocities all live on a sphere that you can map out. I just made a little picture of it there. And this describes the aftermath of a binary collision between particles probabilistically, because it's mapped out by your probability space, which in this case is a sphere. And so this gives us the context to look at the Boltzmann collision operator. So there's the collision kernel that's denoted here by capital B of V minus V star and sigma. And then the collision operator takes the form QFG of V. And it's this non-local integral operator because the integral over V star. So if you have an incoming particle V, then you integrate over all particles that it could collide with V star, and you integrate over all parameterizations of the collision, V sigma, and then you have a kernel B, capital B, and then you have F prime star G prime minus F star G, where this is F prime star is F V prime star, G prime is G of V prime, and F star is F of V star, and G is G of V. So these are all evaluated at the different possible variables that I told you about in the previous slide. And it's actually Maxwell, James Clerk Maxwell in 1866 computed this kernel B from these intermolecular potentials 5R is R to the minus P minus 1 for P between 2 and infinity. He calculated this in his famous treatise in 1866, and he actually did this calculation. And this calculation is actually found in just about every graduate statistical physics book, even today. And you can calculate that B takes the form of V minus V star to the gamma times lowercase b of cosine theta, where cosine theta is a unit vector V minus V star dotted with a sigma, and lowercase b is an angular function. This lowercase b, there isn't a precise, exact closed formula for it. It actually satisfies it's a solution to an elliptic integral equation that's not solvable in terms of elementary functions. It has a solution, but you can't write it down in terms of elementary functions. So there is a unique lowercase b, but you can't write it down in terms of elementary functions. But nonetheless, its behavior can be well understood. And its behavior is sine of theta b of cosine theta is equal to theta to the minus 1 minus 2s, where s is between 0 and 1. So s has a formula that's 1 over p minus 1, and theta can be taken between 0 and pi over 2. And so this, and the kinetic factor of V minus V star to the gamma can also be singular. It has a formula in terms of the p's, and it's greater than minus 3. It's between 1 and minus 3, depending on the value of p. And so in the results that I'll present to you today, we assume that we will decouple the dependence on gamma and s, and we'll assume that gamma plus 2s is greater than minus 3 over 2. And this assumption is satisfied by all of these inverse power intermolecular potentials. So this, the thing I want to emphasize here is that this gives an example of a non-local fractionally diffusive operator that was defined in 1866 before the concept of fractional derivatives was even invented mathematically. But nonetheless, this Maxwell physicist wrote down this equation, and he didn't know it at the time, but he just calculated this lowercase b from a physical potential, and this is what he got. And now this is well understood that this is like a geometric fractional Laplacian. But so for a long time, there was this grad angular cutoff assumption that was used, introduced by Howard Grad in the 1960s. And people just assumed that lowercase b of cosine theta was either bounded or integrable. And this is a reasonable assumption. It's satisfied for the hard sphere case, but it's not satisfied for the inverse power intermolecular potentials, and it's and the behavior is very different if you do that. If you assume the grad angular cutoff assumption, there's no smoothing effects, and this is no longer a fractionally diffusive operator. If you use these singularities, then you get fractional diffusion. Okay, so that is the collision operator. And to emphasize this point, I'll also introduce to you the Landau collision operator. So Landau in 1936, so a while later, Landau, as far as I know, only wrote one paper on the on this equation, and this is the one. And it's from 1936, and he observed that for the Coulomb potential is very important. It's when P is 2 in the inverse power intermolecular potentials. But when P is 2, the Boltzmann equation does not make sense. The Boltzmann operator does not make sense. Landau observed that, and that he wanted a kinetic equation for the Coulomb potential. And so he kind of took the pole of the Boltzmann equation. And so you can take a limit as P goes to 2, and you can derive within the intermolecular potentials, and you can derive this equation, this kernel. So QGH is gradient V integral R3 phi times G of U gradient V of H minus H of V gradient U of G du, and this can be represented as sums. And here phi is this 3×3 non-negative projection matrix. So this quantity in parentheses projects onto the sphere, and then you have this factor V to the gamma minus 2. So the physical case is gamma equals -3. That corresponds to the Coulomb potential, but other cases are studied in the mathematics literature. So for all gamma greater than or equal to 3, you can study this. And so this is a Landau collision operator, and it shows the diffusion. So that because you see whole derivatives in the V variable. But it's degenerate diffusion because this matrix phi projects onto a sphere, and it has a null space. And this factor V, when gamma is -3, is 1/V, so it's a singular. So it adds difficulties that are still, in many cases, not as well understood as we would like. So that's a Landau collision operator. And now I want to talk about boundary conditions. So for this equation, you can have several different boundary conditions. It's not as straightforward as what people may be familiar with, so it's worth talking about. So you have the torus case. The x in T3 is just from 0 to 2 pi, and you assume periodic boundary conditions. So f of tx v is f of t x plus 2 pi ei v, for ei the standard basis vectors and I going from 1 to 3. And in the whole space case R3, you can have suitable decay at infinity, and you can have f of txv goes to 0 as x goes to infinity. That's the usual boundary condition in the whole space but for this model. But you also can have domains. You can have bounded domains. So a domain omega subset of R3 can have general kinetic boundary conditions. You have a domain here, and I call omega interior the interior, and omega exterior the exterior, and gamma is the boundary, and n is the normal vector. And then, so it takes 2 slides to explain the boundary conditions mathematically. So the spatial domain can be characterized as a smooth function. So if you have a bounded domain, you can define it as a set of x such that zeta of x is negative. If omega is connected and bounded, if the zeta of x is a smooth function, and we assume that the gradient of zeta is not 0 at the boundary. So where zeta of x is 0, that defines a boundary, and you assume that the derivative is not, the gradient is not 0 there. Then you can define the outward normal vector, n of x of the boundary, gamma equals the boundary of x, as n of x is the gradient unit vector, so the gradient divided by the length of the gradient for x in the boundary. And then the phase boundary of omega cross R3 is denoted by gamma, and it's the boundary of omega cross R3. And then you typically split the boundary into the outgoing boundary, gamma plus, the incoming boundary, gamma minus, and the singular boundary gamma 0. And you only need to, and these are, so gamma plus, the outgoing boundary, is the set of xv such that n of x dot v is positive. The incoming boundary is gamma minus, it's the set of xv such that n of x dot v is negative, and the singular boundary is the set where the dot product is 0. And it turns out you only need to specify the boundary conditions on the incoming boundary, because the others are included. And so for either the Boltzmann equation or the Landau equation, which we call the kinetic equations, because this also works for other kinetic equations, we have the 4 general kinetic boundary conditions. Inflow is just at the boundary, at the incoming boundary, you specify a function g. A bounce back, this one is in the literature, but it's not typically considered physical. Gamma minus, so f on gamma minus is f on minus v. And then you have the specular reflection, which is f on gamma minus is f of tx and r of v, where r is a projection, v minus 2v dot the normal times the normal. And you also have the diffuse reflection boundary condition, where f on the boundary gamma minus is the mu, where mu is a steady state that I'll define in a minute, times the integral of f dotted with the normal over the set where n dot v prime is positive. So these are the boundary conditions for kinetic equations. It's worth mentioning them so that you can see the whole model. And so I want to mention a point that so a large difficulty to study the initial boundary value problem for the Boltzmann equation is that there can be a singularity at the boundary. And I give the example of this 2017 paper by Guo, Kim, Tanon, and Trust-Gus, where they proved that. And then the singularity can also propagate to the interior of the domain. So this is a very interesting example by Chen-Woo Kim from 2011, where he can, for a specific example of the hard sphere Boltzmann equation, he can propagate a singularity given on the boundary to the interior of the domain. So, so for these kinds of kinetic equations, you really can have singularities, and they can propagate to the interior of the domain. And so it can be hard to study the boundary value problem for kinetic equations with high regularity, because you can have singularities. Okay, so now I'll explain to you the setup in the equilibrium framework. And so we have the steady states for the Boltzmann and Landau equation are these normalized global Maxwellian equilibrium. So mu of v is e to the minus v squared, and it's normalized so that one norm is 1. And then you typically reformulate the solution f as f is mu plus g, where g is mu to the 1/2 times lowercase f. And this mu to the 1/2 here imposes extra decay on the solution, and it also makes the L2 base spaces that you work with Hilbert spaces, which makes things nice. And then the perturbation lowercase f evolves according to this equation here. So TTF plus v dot grad xf is plus the linear operator L of f is equal to gamma of ff, which is a nonlinear operator. And now with our linearization, the linear operator will be self-adjoint in L2. And these operators can be defined in terms of the collision operator Q. So gamma can be defined as mu to the 1/2 Q times square root of mu f, comma square root of mu g. And then the linear operator L can be defined in terms of gamma. So L can be minus gamma f comma mu plus minus gamma square root of mu comma f. And so this is the setup. And this is the equation that we'll study and prove things about. So this is our reformulated Boltzmann equation in this linearized framework. Okay, so but I want to, so there's a lot of activity in studying kinetic equations. And I don't have time to review all of it, but I want to review a few selected results that are very closely related to the theorems that I'm going to tell you about today. And so these are the global existence and uniqueness results in the perturbative framework, so nearby equilibrium, nearby the Maxwellian equilibrium. And so early results in that framework were given by Seiji Yukai, and then a follow-up result with Yukai Asano. So we assume the grad angular cutoff assumption here, and you can take your spatial domain to be either the torus with periodic boundary conditions or the whole space. And then with angular cutoff and with gamma between 0 and 1, Yukai proved in the space L infinity in velocity with a beta weight and HS in the Sobolev space HS with in the X variable with S bigger than 3/2. He proved global existence and uniqueness of solutions, and later this is extended from gamma between -1 and 0 by Yukai with collaborating with Asano in a similar space. So he uses at least 3/2 derivatives in space, and his method of proof was to look for a fixed point of f in the space of continuous functions in X. And a key point is to use the Duhamel representation of solutions, where B is the operator minus V dot grad X minus L, and then you can express F as e to the T B F0 plus the integral of the semigroup applied to the nonlinear term. This is just a Duhamel formulation. And so their method was to prove the existence of a fixed point. Okay, so afterwards, so for the Boltzmann equation with angular cutoff soft potential, so either for gamma between -3 and 0 for the Boltzmann equation angular cutoff, or for the Landau equation, Yang in 2002, 2003. I was actually his PhD thesis student at this time when these results were being finished. Then in the space X in HS for S greater than or equal to 4, Yang proved the global existence of solutions. Later in collaboration with him, we proved the time decay to equilibrium. And the Yang approach was to use a nonlinear energy method. So so in the space X, he would obtain uniform a priori estimates of this kind, where now this norm dx is a dissipation norm for the linear operator. It sort of sharply characterizes the coercivity of the linear operator. And so he proved trilinear estimates. So you have derivatives of the nonlinear term, inner product with derivatives of f, and then you prove these trilinear estimates in terms of the X norm and the dissipation norm. And another key point in this work is to separately estimate the dissipation of the macroscopic parts. So this P of F is these are the fluid variables so you can project the solution into the fluid variables A, B, and C, and then you can derive moment or macroscopic equations for these variables, and they have nice estimates that you can understand. And so these were the approaches to these theorems. Okay, so then in around the 2011, 2012, we had some of the first results for the non-cutoff global solutions to the non-cutoff Boltzmann equation in either the whole space or the torus. And there's this team of AMUXY, Alexander Morimoto, Yukai, Zhang, and Yu. And in the space H4 with this well-known triple norm, they characterize the dissipation in terms of this triple norm, and they can prove the global existence of solutions. And then around the same time, myself with Phil Gressman we proved the global existence of solutions to the non-cutoff Boltzmann equation. And so for the hard potentials and soft potentials from an inverse power law, we use H2 intersect L2. So you use two derivatives in space. And we define this geometric fractional diffusion norm NS gamma. And so this characterizes the geometric diffusion of the non-local diffusion of the Boltzmann collision operator in terms of this metric D, where D is the metric on the paraboloid in one higher dimension, R4 instead of R3. And so I remarked that the Dirichlet form F L of F is equivalent to both of these norms when you remove the null space P. And so these norms are equivalent, but they also have very different representations, and these were two very different proofs of these results. Okay, so recently you have several very interesting and nice results proving global existence of solutions to the Boltzmann equation in the perturbative framework with a so-called mild tail. So you linearize F by mu plus G, where M of V is a polynomial weight times G, and M of V times G is in L1, something like L1 of V, and L infinity in X. So you can have polynomial decay instead of exponential decay in the velocity variable. So you lower the decay assumptions on the velocity variable. There was an early result by Argerighi, Esposito, and Pulverenti in this direction. And then there was this paper by Gualdani, Michler, and Mouhot from, it first appeared in 2013. It was published in 2017 in the Memoir Society of Math France. And it proposes a general method to sort of iterate the semi-group approach and enlarge the functional space. So you start with solutions to the Boltzmann equation in the space where you have exponential velocity decay and the linear operator is self-adjoint, and then you do an iteration and you can enlarge the space and get solutions in with a mild tail. And then there's a bunch of results in this direction. For example, for the Landau equation, there's a paper by Karapatz and Michler, and for the non-cutoff Boltzmann equation, there's these papers by Harao, Tanan-Sriskani, He, Jiang, and Alonzo, San, and Yang. Many of these are published now, but there's a URL where they are in the archive there. And they can prove mild tail in velocity, global existence of solutions to the Boltzmann equation. And again, all these results start by using the results in the with the previous kinds of results with the semigroup and the exponentially decaying velocity, and you iterate to build up to a space with a mild tail. Something that I want to emphasize here is that all of these results use 2 or 3 or 3/2 derivatives in the space. And so I'm counting how many derivatives you use because I want to explain solutions with low regularity. Okay, so now we come to this result by Guo in 2010 for bounded domains. So for the case of the Boltzmann equation with hard potentials, so gamma is greater or equal than 0, say, you can say gamma is greater or equal to 0. Then for hard potentials, Yang-Guo, in bounded domains, Yang-Guo proved the global existence of solutions in an L-infinity framework. So for hard potentials in the cutoff case, you have you can have with bounded domains with boundary conditions that I explained. You can have global existence of solutions in the perturbative framework. And the key was to use L-infinity based spaces. So his approach is different this time. So you have the semigroup. So let f of t equal u t f0, solve the linear semigroup, solve the linear equation u t plus v dot grad x plus L of f equals 0 with initial conditions. And then you can prove L2 time decay here, and then you bootstrap that to get L-infinity time decay. So let L equal v minus k for velocity growth weight. H equals w of f. W is a velocity growth weight. And then you have dt plus v dot grad x plus nu h equals k omega, where k omega is a compact part. And then you do this double Duhamel principle, which was explained very nicely by Vidov in the 1970s. And so you can express the semigroup U as g of t plus integral from 0 to t of g of t minus sk of omega u. And then you can plug in u again. And so you get g of t plus integral g of t minus sk of omega g of s plus this second term. And the key point is to estimate the L-infinity norm of the third term, excuse me. So when you do the Duhamel formula once, this term up here is hard to estimate, but when you do it a second time, this term up here is still hard to estimate, but it can be estimated, whereas the first term it's open. And so this is a nice result, and it's so you see when you do boundary conditions, you use L-infinity. Now, if you want to prove a result like this for the non-cutoff Boltzmann equation, then we still, to this day, don't know how to use L-infinity to prove global existence of solutions for the non-cutoff Boltzmann equation. And this particular approach is hard, and we don't know how to use this approach to do that. Okay, so now I want to, it's kind of unfair, but due to time constraints, I won't tell you about these results. I'm showing you this horrible slide with this very small print, but I just want to emphasize that there's a lot of, there has been a lot of activity on the Boltzmann equation with boundary conditions, with a boundary domain. And so I wanted to show that to you, but I won't really talk about it due to time constraints. But I do want to point out this this result right here by Quoc-Hung, Zhang, and Ouyang that was recently appeared in ARMA on the Landau equation with specular reflection boundary conditions. So they can prove the global existence of perturbative near equilibrium solutions to the Landau equation with a specular reflection boundary condition. And so that's nice. Okay, one more slide on results for the Boltzmann equation. So there have been Bessel space existence theories for the Boltzmann equation with without angular cutoff. So the idea here is to replace H3 plus with space X that's still embedded in L-infinity. And you have this paper by Duan, Liu, and Zhu and ARMA 2016. They proved global existence in the critical Bessel space X equals B 3/2 2 1 for cutoff Boltzmann equation with hard potentials. And then that was extended by Morimoto and Sakamoto to the non-cutoff hard potentials. And then that was extended by Duan and Sakamoto to non-cutoff soft potentials. So they get, so you can have these Bessel space theories for the non-cutoff Boltzmann equation now. And the approach is to use this kind of Schumann-Lerner space. And so you take the frequency projection inside the norm, and then you integrate an L2 in X and V, and then you take a supremum in T, and then you soup over the powers, the 2 to the QS, and the 2 to the QS represent the regularity that you're assuming. And this is motivated by the Schumann-Lerner spaces for treating incompressible Navier-Stokes. Okay, so what I want to explain today is a new space, not a new space in mathematics, but a new space used in the Boltzmann equation to study existence theory. So for a function f to find out the domain omega, the Wiener algebra is a space of functions such that the Fourier transform is in L1. So for example, A of Tn, the Wiener algebra A in the torus is the set of functions f such that the sum over k and zn of the absolute value of the frequencies is finite. And so it's important to point out that we have the following embedding. So A of Tn is contained in L infinity. And A of Tn is a Banach algebra. And so the sum over the modes of the f hat convolution g hat is bounded by the Wiener algebra norm of each term separately. So convolutions, so the object of taking the L1 norm of convolution is preserved in the space. And so something I want to emphasize is that the non-locality of the Wiener algebra allows us to use this space in ways that we still don't know how to do for L infinity in the context of proving statements for the non-cutoff Boltzmann equation. And so non-locality of the space, because you're taking the Fourier transform, helps to understand things. Okay, so I want to, since I'm talking about spaces and I'm telling you about a lot of historical results and the amount of regularity I have, I want to tell you where the space lives. And so a nice example of domain to do that in is the whole space. So in the whole space, omega is R3. We define the Wiener algebra space. A omega is L1 of C, and it's a set of temporal distributions on R3 whose Fourier transform is integrable. And then you have this scale of spaces. So L infinity is the biggest space, and L1, the Wiener algebra, is a little bit smaller, and then the best of space with 3/2 regularity is smaller, and then H 3/2 plus is smaller, and H2 is smaller. So a reason why I'm interested in this space is not just to sort of lower the regularity as much as possible. A reason why I'm interested in this space is because you need to, in order to gain an understanding of the boundary value problems for kinetic theory, you need to have existence theories in spaces where you don't have regularity. You don't have derivatives, because as soon as you have regularity, you can, you expect that your solution can leave the space because the boundary conditions can have singularities, and the singularities can propagate to the interior, as I mentioned early in the talk. And so known examples show that the Wiener algebra L1C space contains bounded and continuous functions with any arbitrarily low order of regularity when regularity is measured using the Fourier transform. And I'll show you an example in a second. So therefore, we think of the Wiener algebra as L infinity plus a little bit more structure. We think of it as a space that does not contain regularity, although it does contain bounded continuous functions. Still, it appears to be an open problem to characterize the Wiener algebra A omega in terms of other function spaces. So as far as I know, and I've asked some experts that if you want to say that A omega is an intersection of known spaces, then that's an open problem. However, Okay, so I'll give you this example. So um, this example actually comes out of my colleague Charlie Epstein's book on medical imaging. In any case, so let phi be a smooth decaying function with phi is like a bump. So the Fourier transform is between -1 and 1, and it's 1, it's 0. It's Fourier transform is 1 when you take a value 0, and the Fourier transform is 0 for c bigger than 1. And then define f hat of c to be the sum from n equals 1 to infinity of phi hat of c minus n to the k plus phi hat of c plus n to the k divided by n squared, where k is a parameter that we're fixing. Then, first of all, for fixed c, at most one term in f hat of k is non-zero. So at most one term is non-zero. So this is n squared is summable. So this function is in the Wiener algebra for every single k. However, unfortunately, f hat of k has best uniform decay rate for all c of a constant divided by c to the power 2 over a of k. So this function decays for uniformly as slow as you would like for any chosen k. So even if you fiddle with this a little bit, you can even get functions that only have logarithmic decay. So here's a function that's in the Wiener algebra that has arbitrarily low regularity. And this function, you can use Fourier inversion, and you can get that f hat of x is 5x times the sum from n equals 1 to infinity of 2 times cosine of n k over n squared. And so this phi can be a very nice function, but this convergent infinite series is nowhere differentiable. And so this function is continuous and nowhere differentiable. And so this is a continuous function in the Wiener algebra that can have arbitrarily slow decay of the Fourier transform. And so you see functions that, so this space contains functions with very low regularity. Okay, so I wanted to explain that so that you see the point of using this space in our existence series. Okay, so recent works using the Wiener algebra in PDE. There's an old paper of Duchamp Roberts from 1988, and then there's a bunch of other papers. So I have worked a lot in this space in the context of other equations, but I haven't gone back to the Boltzmann equation and used it for the Boltzmann equation until this paper. Okay, so here's our space. Now I'm ready to tell you about our theorems. So to study well-posedness of the problems in the perturbative framework, we introduce a function space xt with a finite but arbitrary t. For example, in the torus, xt is L1k, L infinity t, L2v. And so you take the Fourier transform of the solution, you take the L2 norm in v, you take the supremum in t, and then you sum over the Fourier modes k and the z3. And here's the Fourier transform, of course. So this is a Schumann-Lerner type space because the supremum over t is taken before the L1 norm in the Fourier modes. And this feature plays an important role. If you change the order, then you can't do our theorem. Okay, so now we have a macroscopic projection into the null space of the linearized collision operator. So the linearized collision operator satisfies L of G equals L of I minus PG. And you define a dissipation norm. I minus PF dissipation is equivalent to the Dirichlet form of the linearized collision operator. And the LD is defined precisely. In fact, I showed you what the norm is in the non-cutoff Boltzmann case earlier in the talk. And then we define a velocity wave function, WQ theta is e to the Q bracket v to the theta. Bracket v is just growth of v of order 1 for Q and theta. And then we define our norm our energy norm, and then we define our dissipation norm. So the key difference between these two norms is the energy norm uses L infinity in time, and the dissipation norm uses L2 in time. And this norm has a D on it down there. This norm has a V. Okay, and now I can tell you our main theorem. So there exists an epsilon small and a constant C greater than 0, such that for non-negative initial data, if the solution is small, if the initial data is small with a weight, then there exists a unique global mild solution to either the Landau equation or the non-cutoff Boltzmann equation that is remains non-negative. And for t greater than 0, we have a uniform Lyapunov exponent for any t. So the constant C is independent of t. And so even though t is fixed here, it's arbitrary. And the solution is global and unique. So this is our global existence result on the torus. And we also have the large time behavior. So for fixed kappa is a number, there's a formula for it. Kappa is 1 when gamma plus 2s is positive, but kappa depends on the Landau or the non-cutoff Boltzmann collision operator, as well as the weight. And then there is lambda, such a solution also enjoys uniform time decay. So we have uniform exponential time decay to equilibrium. So if gamma plus 2s is positive, you have kappa equals 1. If gamma plus 2s is negative, you have kappa is less than 1. So this is the so-called stretched exponential decay. And so there's two recent numerical studies on the possible sharp 2/3 decay rate. So for the Landau equation with Coulomb potential, when gamma equals -3 and s equals 1, this kappa number is 2/3. And so it's very hard to do numerics and determine a sharp large time rate of decay to equilibrium because anything in the computer is finite. But Sobolev, Gamba, and Zhang, and also Penny and Gamba, in two different numerical papers with two different numerical methods in them, they observe that the decay rate appears to be kappa equals 2/3 above. Although it's a little bit hard to have examples. You can have examples of model problems with a similar behavior that do have this decay rate with 2/3. But so they expand in special functions and they have this big system of ODEs, and it seems reasonable to me. And I expect that their simulations are accurate. So I think that we obtain the sharp decay rates. Okay, so you also have propagation of spatial regularity. Let me not say too much about this, but if you start with spatial regularity, then you can propagate the spatial regularity for solutions. But so in certain cases, we can do better than that. So due to recent work by Imbert and Silvestri on the torus, these solutions experience the C infinity smoothing effect. So our solutions are in L infinity. So they're low regularity solutions. They don't have any regularity. But they're in L infinity in space and time. And you can prove that they have bounded mass, energy, and entropy. And Luis Silvestri, who gave a talk last week in this seminar about his result. So his recent work here and with Cyril Imbert and this nice review article that I posted here proves the C infinity smoothing effect in time, space, and velocity for the non-cutoff Boltzmann equation with hard potential. So in the case gamma plus 2s is greater or equal to 0, conditional to the macroscopic quantities, mass, energy, and entropy being bounded in space and time. plus some additional velocity bounds that were assumed on the initial data. In some cases, like in the case gamma negative. And so our solutions satisfy the assumptions of their theorem when gamma plus 2s is greater or equal to 0. And thus our solutions experience a C-infinity smoothing effect. And there are some technical issues when gamma is negative. Like you have to assume a little bit more velocity decay on the initial data, but you can do that. And so as far as I know, these are currently the lowest regularity global and time solutions to the non-cutoff Boltzmann equation that are known to experience the C-infinity regularization. So previously, there was a threshold of, and at one point it was H5. If you were in H5, then you could get C-infinity, and then it was lowered. This inverse Sylvester result proves that if the mass, energy, and entropy are in L infinity, then you are smooth, and then you're C-infinity. Of course, the proof works with smooth solutions, but their bounds don't depend on the smoothness anywhere, so you can justify all their estimates by approximation. And so our solutions satisfy the smoothing effect. Okay, so in summary, our theorems establish global existence, uniqueness, non-negativity, large time decay rates, equilibrium, propagation of spatial regularity, and for the hard potentials, we have the smoothness of solutions. These theorems hold for the non-cutoff Boltzmann equation and the Landau equation in the space xt without using regularity in the torus with periodic boundary conditions. These theorems will also hold in the whole space with suitable modifications to the time decay rate without regularity. So that's not in our paper, but you can. That's not a difficult generalization given the state of the field. And so we have analogous results theorems in for some boundary conditions. So for some one-dimensional boundary conditions, for example, if you assume the inflow boundary condition on a finite channel, where so you in the x1 variable you have a finite channel, and you allow inflow boundary conditions, and also if you do one-dimensional specular reflection boundary condition, and you assume a symmetry condition that rules out singularities, then you can have a global solution, a global perturbative solution. So that's the summary. So we have a global existence of perturbative solutions, and we can do some boundary conditions. And in some cases, we get the smoothing effects. Okay, so here's the ODE strategy of the proof. So you have the heat equation, and you integrate by parts, and you integrate in L2, and you integrate by parts, and you get the L2 norm decreases, and you can add nonlinear terms, and you can get to the L2 norm decreases. So that's the high-level strategy of the proof. So a key step in the proof is to prove this kind of inequality that we have here. So you have this. This is an energy structure inequality. So you have the energy norm plus the dissipation norm is bounded above by the norm of the initial data times the energy norm times the dissipation norm. A problem here is that in the lower bound you have this projection away from the null space, and in the upper bound that projection did not appear. And this inequality for solutions indicates that as long as one can further estimate the macroscopic dissipation, P of F norm equals the norm of the quantities A, B, and C, where these are the elements of the macroscopic dissipation, then we can obtain a global one-time uniform estimate of the solution under the smallness assumption on F. that can be closed using a continuity argument. And okay, so this is, and we can do this. So this part is actually known from previous work, so we don't have to do that. But what we do have to do are the other parts. Well, I feel like I'm out of time, so maybe I should skip this part. Is that okay?
Okay.
Okay. So yeah, so thank you.